Hi, welcome to the universe of first-order RL circuits. In this video, we will give you a practical and interesting example. The total response of a first-order RL circuit, where there is a voltage source and a switch in series with a resistor and an inductor. The switch K is initially closed, ensuring that the voltage in the inductor UL is 0 and its current IL remains constant. The inductor has a current I0 at time 0. At that instant, the switch K is opened and remains open from that moment on. We want to know what happens to the current and the voltage from that instant onwards, that is, for t equal or greater than 0. In here, you'll find math formulas, some illustrations, and graphs, so you can pause the video whenever you need a little bit more time to let the information sink in. Let's do this. In a circuit with such initial conditions, we have a voltage U equals E for t equal or greater than 0. The differential equation that describes the behavior of the circuit is as follows. In case you want to remember how to get here, you can watch our introduction video to first-order RL circuits. Alright, knowing the value of U, which is E, we can replace it in this equation. Then, to determine the current on the inductor for t equal or greater than 0, we need to solve this first-order ordinary differential equation. First order because it only has the first derivative of one dependent variable, IL, with respect to an independent variable, t. In this equation, E, R, and L are constants, and IL is the unknown. The solution to this equation is the following expression. We can see that this solution equals the sum of the forced response and the natural response of the first-order RL circuit. Both of them are covered in other videos in this collection. Be aware that this solution is obtained through the Laplace transform. We can also determine the voltage across the inductor for t equal or greater than 0, which is given by this equation. Once again, we can see that the total response equals the sum of the forced response and the natural response. Well, but how do we get to it? It's easy actually, through the equations that we went through before. The voltage U is equal to the sum of the voltage UR across the terminals of the resistor with the voltage UL across the terminals of the inductor. Since U equals E for t equal or greater than 0, we can rewrite this expression in the following way. UL equals E minus UR. Knowing that the current through the resistor and the current through the inductor are the same, and remembering, of course, Ohm's law, we have IL equals UR divided by R, which can be rewritten like this. We can then replace UR in the expression UL equals E minus UR. Ultimately, by replacing IL with the equation we saw above, this one, we get our final expression, which is this one. Cutting things short, these are the equations that translate the total response of a first-order RL circuit. But now, let's analyze the graphic representations of these expressions. After a time equaling L divided by R, the current through the inductor with an initial value of I0 reaches 63.2% of the value of E divided by R minus I0 plus I0. this time period L divided by R is called time constant, which is represented by the letter tau. After 3 times that time, that is, after 3 times tau, the current in the inductor reaches 95% of the value referred. And after 5 times tau, it reaches 99.3% of the value referred. On the other hand, the voltage UL across the inductor behaves in the following way. For the instant t equals tau, the voltage UL reaches 36.8% of its initial value E minus R times I naught. At the instant t equals 3 times tau, UL reaches 4.9% of its initial value. And at the instant t equals 5 times tau, UL reaches 0.7% of its initial value. In conclusion, we can see that the initial value of IL of 0 equals I naught, and the initial value of UL of 0 equals E minus R times I naught. We can also see that as t tends to infinity, the current in the inductor IL approaches its steady state, which is E divided by R. And also that as t tends to infinity, the voltage in the inductor UL approaches its steady state, which is 0, showing that UL only has transient state. But let's take a look at another situation. If the switch K is opened at an instant t equal to t naught instead of at time 0, we use the same line of thought with only a few twitches. The current on the inductor will be defined by this expression, and the voltage across the inductor by this one. Therefore, the graphs obtained will be the following, where it is shown that the current in the inductor begins to increase only from the moment t naught instead of at time 0. Thank you so much for staying with us. Keep exploring this universe by watching the other videos we prepared just for you. See you next time and good study session!